Hello. Today I would like to discuss something I discovered in Pascal's triangle. If we mark every pair of adjacent numbers in the ratio of 1 to 2, we'll find something interesting. They seem to be evenly spaced along a straight line. To get from one such pair to the next, we go down into the left 2 and then down into the right 1. And if we do the same thing with a ratio of 3 to 1, we find a similar pattern. These pairs too lie along a straight line, evenly spaced. Let's find out why. When analysing Pascal's triangle, we often use the choose function, which is defined as a choose b is equal to a factorial divided by b factorial times a minus b factorial. For example, 7 choose 3 is equal to 7 factorial divided by 3 factorial times 7 minus 3 factorial, which is 5040 divided by 6 times 24, which is 35. Now, we can see that when we start at that top one in Pascal's triangle, and then go down into the left 7 steps, and then right 3 steps, we reach 35, which is equal to 7 choose 3. And in general, going down into the left A steps and right B steps gives us A choose B. But for this video, I'm going to use a different but similar function, which is defined as f of AB is equal to a plus b factorial divided by a factorial times b factorial. For example, f of 4, 3 is equal to 4 plus 3 factorial divided by 4 factorial times 3 factorial, which is equal to 5040 divided by 24 times 6, which is 35. Now, from here we can see that if we start from the top one and then go down into the left 4 steps and then down into the right 3 steps, we reach 35, which is equal to f of 4, 3. And in general, going down into the left A steps and down into the right B steps gives us f of AB. Now here I've mapped Pascal's triangle onto the Cartesian coordinates, with the top one at the origin and the other ones along the positive x and y axes. As we can see, f of 3, 4, which is equal to 35, can be found at the point 3, 4. And in general, f of xy can be found at the point xy. In this mapping, adjacent entries are mapped to being diagonally adjacent, such as 10 and 5 here. We can see that 5 lies on the point 4, 1, therefore f of 4, 1 is equal to 5. And we see that 10 lies on the point 3, 2, therefore f of 3, 2 is equal to 10. Therefore f of 4, 1 divided by f of 3, 2 is equal to 5 over 10, or a half. From here, if we mark the child at the point 4, 2, and draw a line through this point and the origin, we can see the equation of this line is y equals 1/2 x. And we see that the gradient of this line is equal to the ratio between the two numbers 5 and 10. Looking at another example, 4 and 6, we see that f of 3, 1 divided by f of 2, 2 is equal to 4 divided by 6, or 2/3. And again, the equation of the line that passes through the origin and their child at the point 3, 2 is y equals 2/3 x. Also in this example, the gradient equals the ratio. We could look at this from another way, starting with a number and looking at the ratio of its parents. For a number at the point x, y, its parents will be found at the points x, y minus 1 and x minus 1, y. So what we want to show is that the gradient of the line that passes through the origin and any given number is equal to the ratio of the parents of said number, which would mean that f of x, y minus 1 divided by f of x minus 1, y is equal to y divided by x. By proving this claim, we will show that for any line that passes through the origin, the parents of every point on that line will have the same ratio. Thus, the pairs of any adjacent numbers in Pascal's triangle with a given ratio will lie in a straight line. Proving this claim isn't too difficult. We can show it algebraically. Firstly, f of x, y minus 1 is equal to x plus y minus 1 factorial divided by x factorial times y minus 1 factorial. and f of x minus 1 y is equal to x plus y minus 1 factorial divided by x minus 1 factorial times y factorial. For this step, we can use the fact that dividing by a number is the same as multiplying by its reciprocal. Using this fact, we are able to show that f of x y minus 1 divided by f of x minus 1 y is equal to x plus y minus 1 factorial divided by x factorial times y minus 1 factorial times x minus 1 factorial times y factorial divided by x plus y minus 1 factorial. From here, we can shuffle the terms around to pair up like terms in the numerator and denominator, giving us x plus y minus 1 factorial divided by x plus y minus 1 factorial times x minus 1 factorial divided by x factorial times y factorial divided by y minus 1 factorial. From here, that first fraction cancels down to 1. And since by definition n factorial is equal to n times n minus 1 factorial, the second two terms cancel down to 1 over x and y respectively. Thus we see that f of x y minus 1 divided by f of x minus 1 y is equal to y over x. Therefore, if we choose any arbitrary line y equals mx, for every point on that line, the ratio of its parents will be equal to m. Therefore, the pattern we saw at the start of the video is indeed true, and not just for the ratios 2 and 3, but for every rational number. And we've shown that for any given ratio, the children of pairs of such ratio lie in a straight line that also passes through the 1 at the top, since that 1 was mapped to the origin. I hope you enjoyed the video, and have a great day.